Now, if you remember the run by of the previous videos, I was telling you constantly that we will be throwing a monochromatic light at the prism. Now, what if I throw a particular sunlight, a white light that's been shining on me since a while? So this will lead to dispersion. That is, the refractive index of a particular light depends upon the medium and the wavelength of the light itself. So this will result into beautiful phenomena which all of us know, that is, when we throw a white light on a prism, it splits into 7 colors, 7 constituent colors. So we'll study about that in the dispersion, and also the different natural phenomena which we see, why the color of the sky is blue and why the water looks to be blue or greenish, why the sky looks to be reddish or orange when its sun is settling down or it's rising up. We'll study about all those phenomena in this particular video. So stay tuned a bit more for it. Now let's study about the dispersion. Now dispersion is a very important phenomena which I hope every one of you have come across it. It's majestic, it's scenic, we all love it, we have seen it. It's just a matter of fact that we will now be relating to what we have already seen. So first we'll study about dispersion, we'll then come back to the physical phenomena associated with the dispersion. Dispersion of white light through prism. So I guess most of you have seen this phenomena in the laboratory of yours. That is the phenomena of splitting a ray of white light into its constituent colors, that is violet, right, bluish, indigo, green, yellow, orange, and sort of red. It's called as dispersion. The band of the colors from violet to red is called spectrum VIBGYO. So what we see is in prism, the white light enters and gets split into 7 components given by VIBGYO. So these 7 components, they are called spectrum and have different colors. So the cause of dispersion is basically this. Mu V is equal to sin I by sin RV. I will tell you the suffixes about V over here and over here, and sin R equals to sin I by sin R1. Now mu V and mu R represents the refractive index corresponding to violet light and refractive index corresponding to the red light respectively. It means that for same angle of incidence, I will have different angle of refraction for different types of light. So if I am a violet light or a red light or a green light or a blue light, whatever be my color, it means I have a different wavelength. If I have a different characteristic or a different wavelength, it means I will have different refractive index. That's the property which we come across while dealing with dispersion. We thought that for each angle of incidence, I'm getting a corresponding angle of refraction that's set because of the property of matter. But what we didn't understand is it's very important that we took the wavelength of the light into consideration as well. That is, it's an important aspect in deciding the refractive index for light and the medium. So both play a very important role. So I have this prism, angle of incidence is A, I have a screen over here. Now I will do what I have told you in the previous slide. White light comes in, splits into 7 colors, and this is what we get. If you look closely, I am getting red over here and violet over here. Now violet basically deviates most, right? So it was supposedly about to go in this direction, but right now according to me the violet kind of almost deviated like this. So it's a huge deviation as far as compared to red is concerned. So red, not so good amount of deviation, but violet a considerable amount of deviation. And another important fact which I know about from violet to red is this is the direction of increasing wavelength. So that's the case over here. So again, that's the same thing which I did, that is angle of deviation is getting the whole. So it's del R over here and it's del V over here. So dispersion can also be explained based on Cauchy's equation. Now Cauchy's equation is a very important equation in physics because of one aspect and only one aspect. It relates two of the most important characteristic in ray optics, in wave optics, whatever.
in whichever field of optics you deal with, these will be the two most important aspects of light. That is, one is refractive index, how it behaves when there is a change in medium or new medium, and second one is the wavelength. The wavelength of the light and refractive index plays a very important role as far as light is concerned, its propagation is concerned. So Cauchy's equations related the two most important aspects of light, that is refractive index and wavelength. So your refractive index changes if your wavelength changes, and the relation which governs that change is given by this: mu equals to a plus b by lambda square plus c by lambda to the power 4. A, b, c are the constants. Now just looking by this equation, I can clearly make out that if I increase my lambda, that is if I increase my wavelength, it means my mu will decrease. The value of mu decreases. The value of mu decreases, it means that the value of mu decreases, keeping angle of incidence constant, it means my angle of refraction is increasing, or that is, it's more closer to angle of incidence. So if my angle of refraction increases, that is, I'm not deviating that much from my path, it means there is less amount of deviation. So if you increase your wavelength, your angle of refraction increases, that is, it tries to be more close to the angle of incidence or not to deviate from its path. It means the one with the refractive index of the maximum actually deviates the least because of this relation with the wavelength. So the color gets separated with the different angles of deviation, and violet is most deviated because lambda is very less, and red is least deviated because lambda is very high. For this, mu is very low because it decreases. As refractive index decreases, it means the angle of refraction is very close to the value of angle of incidence. Angular dispersion. The difference in the deviation suffered by the two colors in passing through the prism gives the angular dispersion of those colors. So it's just another physical parameter which we will like to entertain as far as dealing with dispersion is concerned. So there are a few more down the line, so we will have a look about it. The angle between the emergent rays of any two colors is called angular dispersion between those two colors. Another view of looking at the same concept of angular dispersion. It is the rate of change of angle of deviation with the wavelength. So this is how we have further quantified the angular dispersion. That is the third way of looking at it. That is rate of change of angular deviation with the wavelength, which is given by this del V by del R. Then obviously if you divide it by the frequency difference between the violet and red, you will end up getting the angular dispersion, or phi equals to this. That is mu V minus mu R into A. That is, we already know about the angle of deviation for a small angle of prism and small angle of incidence. So we have used that over here in order to find out the angular dispersion. Now there is another physical parameter associated with dispersion, that is dispersive power. Now the dispersive power of the material of the prism for any two colors is defined as the ratio of the angular dispersion for those two colors to the mean deviation produced by the prism. So first, if I want to find out about the dispersive power, I need to first find out about the angular dispersion for any two colors of my interest and the mean deviation produced by the prism. So the ratio of these two will give me the dispersion per unit deviation or dispersive power. So omega is defined as phi by del, where del is the mean deviation as it's written, and phi is my angular dispersion of those two colors. So omega comes out to be del V by del R by del, that is the mean deviation, and finally I will get omega to be omega V minus omega R divided by omega Y minus 1. Why it's omega Y minus 1? Because I'm talking about the mean deviation. So between violet and red, I will have yellow. So the mean deviation is sort of corresponding to the dispersion or mean deviation corresponding to the yellow color. So it can be clearly related in this particular case. Now, the dispersion events which we observe in the nature starts off with a particular theory in the background. So let me put up with the theory, that is how we have used the concept of dispersion, what we have learned till now, in order to reason with the different phenomena which we see in the nature. So the particles of the atmosphere and the other particles that are smaller than the longest wavelength of the light are more effective in scattering the light of shorter wavelength than the light of the longer wavelength. That is, the particles present in the atmosphere, they are more capable of scattering the shorter wavelengths than the light of the longer wavelengths if their size is smaller than the longest wavelength itself. The amount of scattering hence will be inversely proportional to the fourth power of wavelength. So that is a Rayleigh effect. So based on Rayleigh's law of scattering, we come across the event of dispersion. So please keep in mind the assumptions that are being played, that is the particles, they need to be smaller than the longest wavelength of visible light. They are more effective in scattering the light of the shorter wavelengths than the light of the longer wavelengths. Now let's look upon an event corresponding to this. Light from the sun near the horizon passes through a greater distance in Earth's atmosphere than does the light received when the sun is overhead. So what it's trying to say is, when the light is or when the sun is just about to rise up or go down or set, the light kind of caresses the whole curvature of the earth for a while. That is, it travels a longer distance in the atmosphere. It's like in a horizontal fashion. But when the sun is overhead, the light doesn't travel that much amount of distance. So this is one phenomena. Now, based on this, or the answer to this statement, or the reason of this statement, is also the reason why we see the sky to be a bit red or an orange in the evening or in the morning. Correspondingly, the scattering of the shorter wavelengths accounts for the reddish appearance of the sun at the rising and at setting. So it's because of the scattering of the red light that we end up getting those reddish color. And that's the same reason why the light travels a bit a far off distance, and that is the light, a reddish orange color light, which travels a very far off distance when the sun is settling down or coming up. Other case is when looking at the sky in the direction away from the sun. So when I'm looking not directly at the sun but a bit away from it, we receive the scattered sunlight in which shorter wavelengths predominate, giving this color is characteristic bluish light. So as I have told that the sun is actually a great source of light and is throwing light directly on the face of the earth, but there are particles which are very good in scattering the shorter wavelengths if their size is smaller than the longest wavelength. Now, if you go high, the particles which we come across in the atmosphere are of a very small size. So small size which are small enough, or let's say are smaller than the longest wavelength of the light which sun throws in. So there is a scattering of the light, effective scattering of the light which have shorter wavelengths. So the blue being the shorter, predominant, visible light gets scattered most, and that's what we see as a blue color sky. So that's the reason why I have the characteristic blue sky. That's the reason why the sky looks to be blue, because it's of a very short wavelength and gets scattered the most.
So with the help of Prism, I learned completely about dispersion. That is, also about few mathematical quantities were brought up to deal with dispersion, that is dispersive power, net mean deviation and whatnot. So now that we have completely quantified dispersion by coming up with different physical quantities, and have completely learned about dispersion, so it's a complete wrap up of all the optical phenomena which we need to study in this chapter of ray optics. So now we'll shift our attention to the application aspect of these phenomena. So let's watch out what are those applications.